Welcome to a video on solving linear programming problems using Desmos. In this video, we're going to look at how to find the maximum value on a bounded region. Let's get started. Before we look at the example, let's remind ourselves what the fundamental theorem of linear programming states. It states that if the feasible region is bounded, then the optimal solution for the objective function, the maximum or minimum, will occur at one of the corners. If the feasible region is unbounded, then a maximum for the objective function does not exist. If a minimum exists, it will occur at the corners. Whenever you're trying to solve a linear programming problem using the graphing method, it's important to identify your feasible region because you need to know if it's bounded or unbounded, and you have to identify the corners because that's where the optimal value will occur, if there is one. Here's the example that we'll look at in this video. Let's use Desmos to find the maximum of the function z equals 6x plus 17y, subject to the constraints 6x minus y is less than or equal to 48, 3x plus 5y is less than or equal to 90, x is greater than or equal to 0, and y is greater than or equal to 0. Here are the steps on how to solve linear programming problems using Desmos. I'll go over the steps and then we'll use Desmos to solve our example. First, we want to use Desmos to draw the feasible region and locate the corners. Then we'll enter the corners into a table in Desmos and then evaluate the objective function at each corner point. When you do this in Desmos, we use the last column of our table to insert the objective function, but we'll need to replace x and y with x1 and y1. The Desmos graphs used in this video are linked in the video description. Let's go over to Desmos and start by entering our objective function and the constraints on the left side. Open the website desmos.com. Click on the button Graphing Calculator in the center of the screen, or go up to the Math Tools menu and select the Graphing Calculator. When Desmos first opens, you'll have a blank graph. Go over to the left-hand side and enter the objective function and the constraints. As you can see, I've already entered the objective function and the constraints here. Now that we've entered our functions, we need to identify the feasible region. Let's determine the feasible region by locating where the shaded area for the constraints overlap. So I'll go ahead and turn on all of the constraints now. To locate the feasible region, it's usually a good idea to zoom out. You can zoom out by using the plus and minus buttons on the upper right corner, or you can use your mouse to zoom out. So we're looking for where all of the shaded areas overlap. That means the region needs to be shaded 4 times since we have 4 constraints. It looks like these 4 areas overlap toward the center of the screen. If you have a hard time identifying the feasible region, try to turn off the constraints and then slowly add them back one at a time. I'm starting from the bottom up. Here's y is greater than or equal to 0. That's the top half of the plane. X is greater than or equal to 0. That's the right half of the plane. This already eliminates 3/4 of the graph. We know our feasible region has to be in the upper right, which is in quadrant 1. Now let's add 3x plus 5y is less than or equal to 90. That adds another shaded region into the graph. Looks like we're in this triangular area toward the center. And then 6x minus y less than or equal to 48. Our feasible region is going to be a polygon toward the center of the screen. I'm going to use the graph settings to zoom in. Let's restrict our x-axis to be between -2 and 20, and our y-axis to be between -2 and 20. And I'm going to go ahead and lock the viewport. It looks like the corners of our feasible region are going to be 0, 0, 8, 0, 10, 12, and 0, 18. Now that we have our corners, let's add them to a table on the left-hand side. To add the corners, go up to the top left where it says Add Item and select Table. Enter your corners into the table using a clockwise or counterclockwise motion. So I'll start with 0, 0, and then 8, 0, 10, 12, and 0, 18. To emphasize the feasible region, I'm going to add the command polygon x1, y1 into a cell on the left-hand side. Now this area shaded in black is our feasible region. To ensure that this polygon is your feasible region, you can toggle the constraints on and off to ensure that each constraint shares a border with the feasible region. So now we've entered our constraints, we've located our feasible region, we've identified the 4 corners. Now to find our maximum value, we need to evaluate the objective function at each of the 4 corners. To do this, go up to your table where you entered your corners. In the 3rd column, enter the objective function, but instead of using x and y, use x1 and y1 because those are the labels used on your table. So I'm going to enter 6x1 plus 17y1. And now Desmos has evaluated the objective function at each of the 4 corners. Since we're looking to maximize the function, let's identify the largest value, which is 306. So the maximum value of our objective function is 306, and that occurs when x is 0 and y is 18. Let's summarize what we just did. We used Desmos to solve the linear programming problem where we wanted to maximize z equals 6x plus 17y, subject to the 4 constraints. We used Desmos to locate our feasible region and the corners. Then we evaluated the objective function at each of the 4 corners. Since the region was bounded, the fundamental theorem of linear programming guaranteed us that this objective function would have a maximum value at the corners. Our solution was the maximum value of 306 for the objective function, and the maximum occurred when x was 0 and y was 18. That's it for this video. Thanks for watching.